So good morning, good afternoon, good evening, wherever you are. Welcome to Data.SQL.Saturday.LA 2021. Hope everyone is enjoying the virtual conference. I am thoroughly enjoying it. I've been glued to my laptop since the morning. I've learned a ton about SQL Server and a lot about Query Store. So that was very interesting. Hope with this session, we'll be able to spend some time on the Amazon version of Postgres and kind of learn a little bit more on the things that we do differently versus the community version, and also a few recent feature enhancements that we've launched with the service. So before we begin, a little bit about me. My name is Shayon Sanyal, and I'm a database specialist solutions architect at AWS. I specialize in the Postgres engine, so primarily the Aurora Postgres engine and the RDS Postgres engine. And I live and I work out of New York. I love what the city has to offer in terms of its food, its diversity. Love going for hikes. I love the culture and the city views. I also am an avid runner. I do like running long distance. I've done like a couple of half marathons, looking forward to doing a full marathon very soon. I also love my coffee. So my day usually would start with at least 2 cups of coffee, if not more. And my daytime job is to, of course, tinker with everything Postgres. I feel it's the best way to learn anything about Postgres is just pure hands-on, get into it and just start playing around, break things, and that's the best way to learn about it. I do have a lot of handles there, so feel free to connect with me over LinkedIn, Instagram, Facebook, Twitter. My GitHub doesn't have any public repos yet, so maybe I'll fix that post this session. And you'll also find this deck there if you want to just use it later for just keeping it with you, going over whatever we've talked to today, and that'll be there as well. So I'll share all those links with you mostly after the session. I do also encourage you to ask me any questions in the chat, and we will sort of address them towards the end is my preference because we have a jam-packed agenda. We'll go through a lot of content today. It may take some time to peruse through it, etc. So we'll hold on till the end. However, I do encourage you to please start typing questions in the chat, and we'll take them towards the end. So with that, let's begin. For today's agenda, we'll start with a brief introduction to Amazon Aurora. We'll discuss Aurora's distributed storage architecture. Then we'll cover two important points on how we handle the highly available and the failover, as well as which is the in-region resiliency, as well as the cross-region resiliency. Next, we'll take a look at a few key features of Amazon Aurora Postgres. We'll then cover security, monitoring, migration, and finally, we'll wrap it up with some new additions to the platform that have been recently announced. So let's start with a short background on Amazon Aurora. So Amazon Aurora is an enterprise database built for the cloud. It has the speed and availability of high-end commercial databases, and it has the simplicity and cost effectiveness of open source databases. This basically means that there is no licenses to manage. There's no licensing cost. It's also drop-in compatible with 2 open source relational database engines. You can either choose the MySQL version or the Postgres version, and which basically means that this code that you wrote for either of these databases will continue to work with Amazon Aurora without making any changes. And of course, all of this comes with the AWS promise of simple pay-as-you-go pricing. So that makes it a little bit easier. Now let's take a look at the shared distributed storage architecture. So Amazon Aurora has a purpose-built log-structured distributed storage under the covers. And what you see here is your storage volumes actually get striped across hundreds of storage nodes. And here on the slide, you'll see the bottom part of the slide with the orange boxes represent these storage nodes. These nodes are nothing but these are machines with processing power and memory. They have their own locally attached high-speed non-volatile memory express or NVMe SSDs. And the database itself doesn't know the intricacies of this storage. So basically to the database, this is just a simple representation like a clustered storage volume. We also continually back up and stream the data and the logs to S3 for additional durability, which actually makes it highly durable and inherits the 11 nines of durability from S3. So a little bit deeper into it, as part of the distributed storage architecture, we replicate the data 6 ways, and each page is actually replicated across 3 availability zones with 2 copies in each availability zone. And folks who are not familiar with availability zones, basically these are collections of 2 or more data centers which are distributed across 500 miles of each other. So this helps us survive failure of an entire availability zone plus an additional failed zone. We segment the storage volume into 10 gig protection groups, and each protection group is made up again of 6 10 gig segments. And these are the 6 copies of replicated data that we discussed earlier, 2 in each availability zone. With Amazon Aurora, storage scales automatically in 10 gig increments. And in fact, we go all the way up to a maximum size of 128 terabytes in the storage space. Now let's talk about in-region resiliency. We are not talking about across the continent data transfer. We are just talking about one region. And remember that within the region, Amazon Aurora Postgres or MySQL is automatically distributed within 3 AZs, availability zones. So in terms of highly available architectures, of course, we have the native backup and restore capabilities, and Aurora backs up your cluster volume automatically and retains the restored data for the length of the backup retention period. So the way that we differ from traditional or native Postgres backups is that Aurora backups are continuous and incremental. So you can basically uh, quickly restore to any point within the backup retention period. There is no performance impact or interruption of database service as your backup data is being written. So you can specify a backup retention period anywhere from, let's say, 1 to 35 days when you're creating an automatic backup. When you create or modify a DB cluster, your backups are stored in S3 with 11 nines of durability. If you want to actually maintain a backup for greater than the 35 days, you can do something called a snapshot. And these snapshots are, again, these are taken from your cluster volume. And because Aurora retains this incremental restore data for the entire backup retention period, you only need to create a snapshot for data that you want to retain beyond that backup retention period. And for you to restore this database to a new database cluster, the continuous and incremental nature again comes in handy, because what you do is basically restore that point in time backup, and you don't need to take any frequent snapshots. You just need to take the most recent incremental backup or a snapshot, and then restore that, which is where your entire cluster volume gets restored to a DB cluster. You of course have to restore it to a new DB cluster, so do keep that in mind. The next aspect about highly available architectures, and when we are talking about highly scalable and highly available architectures, is the replicas, the Aurora replicas. And Amazon Aurora today, we support up to 15 database read replicas. These are nothing but compute instances to scale out your read traffic. So basically, the replicas would share the same underlying storage as the source instance. And what we do is these are pointing to your same storage. These are pointing to 1 or more copies of your 6 copies of the data storage in the shared cluster storage volume. And it gives you quite a lot of benefits in terms of both availability as well as performance. So in terms of availability, the failing database nodes and processes are automatically detected and replaced. We have an inbuilt database and instance monitoring system, which is where we take care of these failing nodes and replace them without the end user coming to know of it. Replicas are automatically promoted to primary if needed. So from the previous session, there was a question around automatically failing over. What are the tools? So within Aurora, we actually do this automatically within the region. So anytime you have a read replica, that not only helps you scale out your read traffic, that's definitely one purpose, but the other purpose is it can actually serve as your failover target, which is basically where it can take on the role of a primary database node and start serving reads as well as writes in the event that there is a failover or a failure with the primary database node. In terms of the performance, of course, there's you can actually scale out your read traffic and split it across these 15 read replicas. You connect to these read replicas, which we'll talk about in the next slide, through something called as a reader endpoint. And this reader endpoint is automatically load balanced. So anytime you have an ad hoc reporting query versus a data science query, you don't really need to choose which node you want to point to. You have that capability as well. However, you just get to, from the application connection standpoint, you just need to make sure of using that reader endpoint, and that will take care of automatically routing that read traffic to the right node, whichever is closest in terms of the geolocation, in terms of the availability zone, network traffic, and so on. Tolerating compute failure. So what happens in case of a failure? So we talked about a little bit on the instance monitoring and the health checks inbuilt into the system. The Aurora storage as well is self-healing, meaning that data blocks and disks are continuously scanned for errors, and they are replaced automatically. You can assign a promotion priority tier. We call this priority tier within the naming acronym architecture to each instance on your cluster. So whenever your primary instance fails, the Aurora will actually promote the replica with the highest priority to primary. And if there is a contention between two or more replicas in the same priority tier, then we will promote the replica that is the same size as your primary instance. And when we are talking about size, it's basically if you've worked a little bit with AWS instances, these are your R5s, R5XL, R52XL, basically the same class and the same family of Intel processors. We also provide a cluster endpoint, which you see on the screen in purple. This is your primary connection endpoint that connects to the current primary instance for their database cluster. And this endpoint is actually the only one that can perform write operations, including things like inserts, updates, deletes, DDL changes. You can, of course, also use this for read operations. However, you also get a separate dedicated reader endpoint, which is what you see in red on your screen, which basically is the one that we talked about previously. This is used to load balance your read-only traffic to one or more read-only replicas. So anytime you have a reporting query, anytime you have a data science query, anytime you have a similar query that you want to run on your primary instance, but you don't want to overwhelm the primary node of the cluster, you can run this on the reader endpoint using the reader endpoint, and this will basically give you those results. The last point about improving high availability, we launched a service, I believe this was 2 years ago in reInvent, RDS Proxy. This is basically where we do have a fully managed, highly available database proxy service that makes applications more scalable, more resilient, and more secure to database failures. And primarily RDS Proxy, the service itself, offers you 3 distinct benefits. One, and the first and foremost, is connection pooling. This is where you can use RDS Proxy to build more scalable applications, where RDS Proxy will allow you to pool and share connections established with the database. And this will improve your database efficiency. This will improve your application scalability. You don't have to actually drop connections and reestablish those connections. You would know, or probably if you don't know, connections to the Postgres database is actually pretty expensive. And anytime you're opening up a connection, you are incurring a little bit of cost in terms of the resources utilized. So you're actually utilizing a little bit of CPU, you're utilizing a little bit of memory, you are utilizing, of course, network traffic to establish that two-way handshake communication. So anytime you have these connections, new connections open and close, a lot of the times in production workloads primarily, these become expensive. So connection pooling comes in as a solution where you don't need to, your application does not actually need to open these and close these, open and close these connections all the time. You basically have this pool of connections where you can reuse the existing connections and you don't need to actually open and close all the time. The second benefit is minimizing failover disruption. So just conceptually, if you think about it, RDS Proxy sits between your applications and the database. So all the connections from the applications are are in fact to the proxy. So whenever there is a failover, the proxy will persist those connections while the failover occurs. And then the advantage is your application does not actually need to reestablish those connections. So your proxy will help and reconnect automatically to the standby database while it's failing over. And in the process, you're getting more resilient applications because you're not dealing with any more DNS endpoints. You're not dealing with any more DNS flushing. So you're essentially bypassing that. And proxy is continuously maintaining what's the health of the database at any given point of time. And by doing that, it can do such failovers much quickly. The third is improved security. So you can, of course, build more secure applications. And this comes with the platform. So basically, we have full integration with IAM, which is the Identity and Access Management service in AWS, as well as Secrets Manager. So all your credentials, database credentials, are stored in Secrets Manager. And you use your IAM roles and policies for accessing any other resources like you do regularly for your database. No need to embed any usernames and passwords in your application side. No need to have automatic rotation, any custom automatic rotations enforced. Secrets Manager will actually do automatic rotations for you. And of course, lastly, it is delivered as a fully managed service. So it does give you that benefit as well, where you don't actually need to be a DBA and go in and log in and change a bunch of config settings and manage it end to end for you. Next, let's take a look at cross-region. We looked at in-region. Now let's take a look at cross-region resiliency. All right, so this is where we actually talk about something called as a Aurora Global Database. And typical use cases you might have come across critical workloads, specifically in the financial services industry and also any hyperscale industries. You'll see they will have a global footprint. This is travel, this is gaming. They always have strict availability requirements. There will be a strict need to tolerate a region-wide outage. And traditionally, this required quite a lot of difficult trade-offs between performance or availability, cost, data integrity, etc. So what we've done to address some of those requirements are with a global database. We launched this a couple of years ago. And the way it works is it's designed for exactly these kind of globally distributed applications where we are allowing a single Amazon Aurora database to span across different AWS regions. And with global database, we'll replicate your data with no impact on the database performance. And we'll enable fast local reads with low latency in each region and also provide disaster recovery from region-wide outages. So those are the two primary use cases for global database. Under the hoods, we do use storage-based replication with typical latency of less than 1 second. This is possible because of dedicated infrastructure that leaves your database fully available to serve application workloads. And in the unlikely event of a regional degradation or a regional outage, one of the secondary regions can be promoted to read and write capabilities. And we'll look at how this works in the next one. So here you'll notice this is my primary region on the left. I have 3 availability zones. So my storage is, of course, automatically distributed across these 3 AZs in the region. And then within the primary region, I have something called as a replication server. And this is a fleet of replication servers that's actually responsible for doing the storage-based replication to the secondary region. And here, one of the examples is consider this as Europe and consider this as the US. So in the secondary region, you have a replication agent, which is another set of fleet of servers, which is again sitting there listening to changes from your replication server in the primary region and responsible for applying those changes to your secondary region. So the number one step here is your primary instance. Anytime you are actually have your global database provision, this is how it will work. So your primary instance will send the log records. We call these as walls, write ahead log, or you can think of it as redo logs or transaction logs. We send these log records in parallel to the storage nodes, to the replica instances, as well as to the replication server. So three-way parallelism is the first step. The second is replication server. This replication server, this red box will be actually responsible for streaming these log records. These are nothing but changes that are happening on your database, the wall files, to the replication agent in the secondary region. The third step is this replication agent in the secondary region will start applying these log records or wall files in parallel again to the storage nodes here in the secondary region, as well as the replica instances. And then finally, the replication server here. This will pull log records from storage nodes to catch up after outages. So anytime if there is a failure and we look at how that's handled, if there is a region-wide failure, the primary region will actually start applying all the changes in the wall files to the replication server in the primary region first, and then stream those over to the secondary region while the secondary region is coming up and trying to be the new primary region. So I want to talk about here a new feature we recently added to Aurora Global Database called Managed RPO or Managed Recovery Point Objective. This managed RPO feature is actually controlled through a database parameter called Global DB RPO. And you might hear when you're coming to Postgres brand new, let's say if you're moving from SQL Server, a lot of these parameters which you'll see in the open source community Postgres, which are controlled in your postgres.conf file, the configuration file, those are controlled both in RDS and Aurora Postgres as database parameters within the AWS world. So we create something called as custom parameter groups and then modify these parameters to reflect any customizations we want to be included for our Amazon Aurora databases. So basically, we give you the central place to manage these parameters. You don't need to log in as a super user to make any changes to the configuration files, etc. So a global DB RPO parameter is basically there to control this. And it'll let you control how far behind you're willing to let your secondary databases lag from your primary database. And let's actually take an example to understand this. So in this example, you'll see this metric RPO lag in milliseconds. This is around 2, and then RPO lag in milliseconds 1 for the other secondary region. So here we have a global database operating in one region, one primary region. We have two different secondary regions, so region 2 and region 3. So basically here the consider the global DB RPO parameter is set to 20. And anytime the secondary databases are lagging by, in this case, they are 2 and 1. Anytime it passes that parameter threshold, so 21 seconds, let's say, there will be a change in action, and we'll see what happens there. So anytime it's less than the threshold, so less than 20, managed RPO hasn't kicked in yet. There is nothing for the managed RPO to do at this point yet. But let's see as time progresses, things have changed. So we have written more, of course, data to the Postgres primary database, primary region. There's maybe a ETL job, or maybe there's a bunch of scripts that were loaded. There's a lot of data that was loaded, a batch job that was executed that overwhelmed the primary region. And there was a little bit of replication lag to the secondary region. In this case, both of the regions are actually behind that global DB RPO metric. So in one region, it's 30 seconds, and the other it's 21, which has actually crossed the 20-second limit. So let's see what happens in this case. So here, managed RPO will kick in. And essentially what it does is it controls the situation by blocking transactions from committing on the primary database. So you'll see that the transactions will get paused momentarily. And till at least one of the secondary regions catches up to be within that 20-second window in terms of the replica lag. This means that queries and reports and your selects will continue seamlessly. There's no connection lost. There's no select queries being lost. But any attempt to make any changes, basically, if you are trying to insert, update, delete any rows from the table in your primary region, that will be paused until your secondary regions are caught up. And we do this, of course, to maintain integrity. We want to make sure there is an RPO of 0. So essentially no data loss. And as we move forward again in time, you'll notice that one of the secondary regions, in this case, region 3, will fall below the 20-second metric. And it'll now be, let's consider it's at 15. So whenever this one of the secondary region catches up to be inside that window, then managed RPO will allow these transactions to start processing again on the primary database. And this parameter, do note that this is available for just Aurora Postgres. And this is the primary driver for financial services customers who have strictly regulated workloads. They have strict RTO, RPO requirements, and they want to ensure that they minimize data loss in the event of a regional outage or a failover event. So you can literally control that this is going to be my RPO. This is 20 seconds is going to be my RPO. I cannot afford anything to go out of order or out of the sequence in my transactions beyond that 20 seconds. So this is where you'll actually be able to designate that time, control that time, and allow those changes to fall through in your secondary regions through global database. Now, earlier this year, we actually recently launched a managed planned failover feature. And this was, again, to deal with situations where you have a global region outage, region-wide outage, and you need to actually fail over to the other region. Primarily, the term that we use here is managed and planned. So those are the key sort of terms to look into it. There is the understanding, of course, not a lot of the times when a disaster happens, it's of course unplanned. However, the feature that we are going to be launching for that is going to be coming pretty soon, not really there yet. However, the planned failover feature is for typical use cases where imagine that you need to perform disaster recovery drills on your production database. A lot of the times, I have come across situations where customers would need to relocate the primary database cluster to a different region, primarily like a disaster a data center rotation policy 6 months, and then fail over to the other region, primarily like a blue-green deployment. They'll have the minimum stack, the application stack up and running, ready to go in a pilot-light fashion in the other region. And anytime that 6-month limit is met, basically they'll fail over their database to this region and have the secondary region serve reads and writes and become the primary database. Of course, this is typically useful for those use cases where we give an automated way to do this through the console, through the API, through the SDK, as well as through the CLI to promote your secondary region to a primary region. And it's possible through the console with a click of a few buttons. And basically, you have your ability to test your DR setup and relocate your primary region with managed plan failover. Of course, we do have an RPO of 0, so there is no data loss anytime your new primary is being promoted in the time that your new primary or your old secondary is being promoted. Writes are stopped completely on the primary region, the old primary region, until your new primary or the old secondary region catches up. And this is again based on the replica lag. And in this example, we'll see a quick walkthrough. So your primary region is actually Ohio, and two secondary regions are Northern Virginia and Ireland. So once we click, and your app is of course pointing to your primary region, which is in Ohio. So we'll click to promote one of the secondary regions. In this case, it's going to be US East 1, which is Northern Virginia. In this case, when the managed plan failover is going through, the writes are stopped on the primary database region. Your secondary regions catch up on whatever changes happened, the latest transactions that were committed. Those are applied, and how they are applied is through those replication servers and agents. The Northern Virginia, which is the new primary, becomes the new primary. So basically, there's a flip between the old primary and the new primary automatically. And then writes are now available in the Northern Virginia region. And finally, once it's up and running, you have your database available in the status as available. You point your app to your new region, the new primary or the old secondary, and you're good to go. Now let's glance through a few key features in Aurora Postgres. There's a lot to cover. Of course, I won't be going through a lot of these. However, we'll cover a couple of these in depth. But the distributed storage engine itself, if you think about it, provides quite a lot of benefits. And it does things like wall log processing. It does instance crash recovery. It does It is fault tolerant and self-healing by the instance monitoring and health check, which is implicit inbuilt into the system. We have something called fast database cloning, which we'll look at what that means. You have your regular database snapshots, you have your restores, point-in-time restores. The difference from Community Edition Postgres, remember that these are continuous backups, and you can do point-in-time literally to the second when you're restoring these backups. So there are no scheduled, there's no dependency on scheduled backups, etc. There is storage automatic scaling independent of compute. There is compute scaling in terms of read scalability. We also have auto scaling groups for compute instances. We do have a feature where we provide a warm cache on database restart, providing better performance actually for fast failovers, as well as low latency replication. And we'll look at all these a little bit in depth. So beginning with logical replication. And Ryan, in fact, in the previous session, touched upon a little bit on it. I did want to get into it. So with Postgres Community Edition, so logical replication is a method. It was introduced in the community version starting with Postgres 10. So we are talking about native logical replication. So in the native logical replication, what happens is it's basically a method of replicating data objects and their changes based upon a replication identity. And this is usually a primary key. This is typically a unique constraint, unique index. And the same thing is supported in Aurora Postgres. However, since we have things a little bit differently set up, you use your logical replication in Aurora, rather than going to a config file and making changes, you would actually enable logical replication parameter. There's a parameter called RDS.logical replication in the parameter group for the cluster. Just enable it, set it to 1, and then you set up the publisher and subscriber. So that's basically it. That helps your Aurora Postgres cluster know and understand that you can now basically flipping that switch to use native logical replication. And if you look at the diagram here, and you can look at the database tier, which basically comprises of your SQL layer, your transaction layer, and the caching layer. And we've separated that out from the storage tier, which is basically what happens is you're writing your redo wall records to storage from your compute instances or your database tier. It goes to the storage tier, which is where the storage tier materializes these wall files or the log records into replication slots. And we have this concept of a logical decoder in Postgres. So these logical decoders actually are, you can think of it as a tap to a bucket or a funnel, where you are actually now responsible for opening this. By opening this tap, you're actually publishing these changes. These are your wall records from the replication slot by using one of these decoders like test decoding or wall to JSON or decoder raw to one of the multiple subscribers that you have. So basically, this is how your changes are propagating from one. You can think of it as a source to target. You can think of it as a publisher to subscriber, depending on whichever database you're familiar with. But these are the concepts that we use in Postgres. Now, native logical replication, of course, was supported with version 10 in Community Postgres. There is also an extension, and we talked about a little bit what extensions are. Basically, these are external, you can think of it as external libraries that add or enhance capabilities of your Postgres database. So pglogical is actually one such extension which builds on the native logical replication. It can do quite a lot of what native logical replication already does, but also it adds a little bit more since it's an extension. So you can think of it as a little bit enhanced version of native logical replication. So examples are it can actually do something like conflict detection and resolution. It can actually do bidirectional replication. So you can have a publisher and a subscriber, Amazon or a Postgres database, and you can do two-way or a multi-writer uh, two-way setup where you can do basically publish changes from the source to the target, and you have your source and target set up as publisher subscriber. You can also have the source and target reversed, and you can have the target set up as a publisher and your source set up as a subscriber. And you can basically have your bidirectional replication work using pglogical and conflict detection and resolution. So those are the two replication capabilities, very powerful. Although they do have quite a lot of restrictions, do have a look at those restrictions before you actually implement that. And then we are talking about fast database cloning. So fast database cloning, the typical architecture of Amazon's Aurora, which is a distributed storage engine, allows us to do things which are normally not feasible or cost efficient with a traditional database architecture. And with fast database cloning, what we've done is we've created these pointers to individual pages of data in the storage engine itself, which enables this feature called fast database cloning. So anytime you make changes to the data in the source or the clone, a copy on write protocol actually triggers creation of a new page in the disk and updates these pointers. So what this basically means is anytime you have your 2 terabyte or your 10 terabyte snapshot restore job that used to take an hour or maybe days to restore your production database to a new cluster, this will actually now be ready in about 5 minutes or so. And because we are doing this with the pointers, there's no need to recreate the cluster from scratch. Anytime you have changes on your cloned cluster, that's the only time we are writing these changes to the new cloned storage. And we are breaking those links from your primary production database. So your production database is isolated. It's not impacted from changes on the clone. The clone is doing its own separate workload. So basically use cases would be if you have a dev test where or a QA workload which needs to test on production like data sets, this is where you'll use it. If you have analytics, you have a select, sum, count, min, max, order by, group by. Rather than impacting the OLTP or the transactional data store, you can spin up a clone very quickly and do your analytics workloads on it. Of course, this is medium level analytics. We do have Redshift, which is for very high volume data loads and analytic workloads. So do leverage Redshift for humongous data volumes, but for light and heavy, light and medium workloads, you can use you can pretty much leverage the clones with Aurora Postgres. You can also use it for running benchmarks, things like comparing performance on production versus your QA, etc. The next feature is cluster cache management. So this is where we do provide a fast failover capability. Basically, the way we do this is we have a failover priority, which we saw. And I'll actually skip through the animations here quick. So here you have your read-write instance in one availability zone set to priority 0. And remember, one of the read-only nodes, if it's set to the same priority, it actually makes it eligible to be a new failover target. So anytime anything happens with your read-write node here, your failover priority 0 will tell Amazon Aurora to failover to this automatically. So this happens automatically. There's no DNS change included at the application level. You don't have to worry about changing any endpoints. It's the same endpoint that you were using previously. It'll point just under the hood to the new node. And this read-only node will take on that role. And the way it works is we'll basically start shipping a Bloom filter of the replication cache that's in the read-only node to the read-write node. And the read-only node will basically tell the read-write node that here's what I have. And the read-write node, when it receives it, will say that here's what I have, and here's what you need to load. So basically the delta. And in the background, asynchronously, It doesn't block any replication channel. We slowly load this stuff and typically get about 80 to 90% memory match. And when we are doing this. So this helps with reducing your cold start times in the event of a failover to this new read-only instance. Of course, you enable this with another database parameter called apg enable and just turn it to on. By default, it's off, so just need to set it to on. Of course, performance benefits. So you can think of this as typically you'll see this where your CCM is enabled. Let's say in this slide, what we did was run a PG bench. PG bench is of course an open source, freely available benchmarking tool. And here we are running this with 20x read only mix and a 1x read write mix for a 160 gig cached workload. And we are failing over at the 10th minute. So the moment you're getting around, let's say we are running a workload, we are getting about 300K, more than 300K TPS on your system. And we failed over at the 10th minute or 600-second mark without CCM enabled to get to the same level of performance. This is your, you can think of it as a light pink line. This is the time it takes basically. So with baseline with no CCM enabled, you are about 340 seconds actually to get to the same baseline performance. Whereas if you have CCM enabled, you'll actually reduce that by 90%. You are getting up to 32 seconds to get to the same level of performance with CCM turned on. So that's the performance benefit of a warm cache in the event of a failover. Now, the next improvement that we've done is query plan management, and this is primarily you can think of it as a feature to help your Aurora Postgres database have predictable query plans. So it basically gives you two things. It's plan stability over time, as well as plan adaptability. So anytime your plan changes, anytime you have more data into the table, you have more indexes created, your cost will actually change for executing a query through one particular plan. And anytime you want to make sure that you want to use the same plan, which was probably minimum cost, you can set it to run with the same plan that it used to run. So with query plan management, again, it's a DB parameter setting where you'll just turn it on for the cluster. And anytime you have a plan, you need to use a plan which was probably the least cost for a query. It'll keep using that regardless of the new indexes created. And in case it does see a lower cost plan due to the new index created, it'll automatically detect that and it'll set that as a baseline for new queries which use that plan and start using that. So pretty nice feature to have where you need to ensure stable plans and you don't need to get into plan regressions, etc. Getting a little bit of background noise if someone can mute themselves.
This is just going to create the device in your IRPO. When it's created, you're going to actually go and click on it. As you can see, I named the address 4. I have a primary key here, a secondary key here. This is my connection string, so I'm going to actually
Should we
copy it from here.
wait for a little bit?
Okay, I think I need to find who I need to mute. Give me a second. Sorry.
Sure. Yeah.
So to do that, the installation is actually done. The one that I was showing you was IoT-H.
Oh, we have mute. Oh. Okay, I think somebody is attending multiple sessions. Smart plan. Go ahead,
right.
sorry.
Yep, thanks, Steve. All right, so the next innovation from the Amazon Aurora space was integration with the machine learning stack. So of course, we have a whole different world of machine learning services. And there are two distinct services that we, in fact, have integrated with. And these are SageMaker and Comprehend. So essentially, with Aurora integration with these services, what you can do now is you can pretty much have your SQL programming language. So you don't need to learn any new query language. You don't need to have any prior machine learning experience. What we do is you use these simple optimized SQL functions for SageMaker and Comprehend to do things like sentiment analysis. You can do things like fraud detection. You can do things like product recommendation, targeted marketing, etc. And this is basically your SQL functions that you're running, and this function is going to your uh, SageMaker and Comprehend services, running your model there, and then just fetching those results back to your database. So a pretty useful feature for people with no machine learning experience. The other thing is, of course, Serverless V2, which is currently, I should highlight, is in preview for MySQL only. And it's going to be coming soon in GA for Postgres as well as MySQL. So there's not going to be any preview for Postgres version. There's going to be a GA version directly. However, if you want to play around, give us some feedback on the MySQL version of V2 serverless. Please feel free. I'll share links towards the end where you can sign up for the preview and you can get going. So serverless V2, of course, builds on the V1 advantages, and it has been architected from the ground up to support serverless clusters that are instantly scalable. And this is basically resting on a lightweight foundation that's engineered to provide security and isolation that you need primarily in multi-tenant serverless cloud environments and microservice architectures. So anytime your developers don't have a lot of background in or don't want to manage a lot of database servers, with the provisioned versions, provisioned Aurora server, Aurora Postgres versions, you can actually leverage these serverless clusters where we maintain a warm fleet of instances. And anytime you throw workload at it, we automatically scale up, scale down in basically Aurora capacity units. These are the metrics that we use for scaling up or down. Uh, and these are finer granular controllable in the V2 version versus V1. So this foundation has very little overhead, so it can respond very quickly. And it's also pretty powerful to meet dramatic increases in processing demand.
Shayon, there's a question from the audience. Is your last slide of Query Optimizer enabled by default, or does it need to be enabled?
Yeah, so the QPM query plan management, this needs to be enabled. This is off by default, and this needs to be set on in the database parameters.
Cool, thank you.
Yep. So Babelfish. So Babelfish, of course, we saw this a little bit in the previous session. Babelfish is a new translation layer for Amazon Aurora Postgres that enables the Aurora database to understand commands from applications which are actually written for SQL Server. And this is where you will actually see that the Aurora Postgres database now understands T-SQL. There is a little bit of change required from your application connection standpoint. There is your SQL Server's proprietary SQL dialect is being leveraged. We support the same communication protocol so that your apps can connect seamlessly to the Aurora Postgres engine, which used to be written for SQL Server. As a result, the effort required, there is an effort required. However, the effort required to modify and move applications running on SQL Server to Aurora is reduced. And this leads to a little bit fast, a little bit lower risk, and more cost-effective migrations. You do have, we do offer the AWS database migration service, of course, and the schema conversion tool for primarily doing a dump of your schema from SQL Server to Postgres. You can use that to create indexes, constraints, secondary objects, and so on and so forth. But often from the application side, when you're rewriting these applications to connect to a different database, there's a lot of work that goes in. And Babelfish is actually a step in that direction to make it a little bit easier for developers.
Shayon, this is probably a follow-up question to question before. Then you enable the Query Optimizer. So any risk of enabling it?
No, so there is no risk of enabling it at the cluster level. Essentially, what's just going to happen from a storage footprint is Since those plans, the query plans are actually being persisted in your storage in the database itself, your storage volume is actually growing. Although it's incremental, it's very tiny. Your storage plans are being stored there and they are growing over time. So anytime you have more indexes thrown into your database, you are incurring a little bit more storage footprint. So the best practice is, of course, to get rid of plans. You can use a function called delete plans which are no longer required, and you can just call that function to delete those plans which are no longer required. In terms of performance, since you are setting that as a baseline plan, you don't have to. Your optimizer doesn't have to actually pass through a bunch of plans and get to that plan because it already knows that this is the least cost plan. This is the first that it'll go to and pick up for executing that query. So only in terms of the storage, there is a minimal storage footprint that gets incurred because you're, of course, adding to more plans. You're storing that in the disk. So anytime you have it enabled, do make a note of plans that are no longer used. Just get rid of that by using the delete function.
Okay.
Cool. All right. So the next thing that we are doing with Babelfish is, of course, we are going to be announcing this as an open source project. It will be available on GitHub. It will be available for any purpose. You can pick up the source code. You can add your enhancements. You can contribute to help steer the direction by giving feedback. You can do your basically community-driven roadmaps. You can meet your purpose, whatever purpose suits your goal. It will be distributed under the Apache 2.0 license and will be available sometime in 2021 towards the end. I don't have the date for it, but be on the lookout for the preview page, which will actually have the most recent updates for making it open source. There is, of course, federated query for Athena as well as Redshift with the integration on Amazon Aurora Postgres. So with Athena, you can actually run SQL queries across data stored in relational, non-relational, object, and custom data sources. And we actually use data source connectors, and we've open sourced these data source connectors for JDBC compliant relational databases like Postgres under the Apache 2.0 license. So you can use these connectors, and these connectors actually run on Lambda. So there are no servers to manage. It's a serverless provisioning way to actually run your federated queries for your structured, semi-structured, non-structured, unstructured data sources across various stacks. The second one is Redshift. So similar to Athena, we also have integration with the data warehouse in Amazon. So you can literally leverage your data lake. So your S3 as your data lake. You can have Aurora Postgres as your transactional database, and you can have Redshift as your petabyte scale data warehouse. And then you can push down the queries at your different sources. So basically, you can push down predicate processing at your transaction layer with Postgres. You can have your S3 join with that data in the transaction layer, and you can join it with Redshift and then run reports out of it. Quite a lot of flexibility actually with Redshift federated query. We also recently announced Graviton 2 R6G for Aurora Postgres. So these are, of course, we have custom built these with 64-bit ARM Neoverse cores, and this delivers better performance, higher throughput, and of course, much more gives you much more price performance benefits. We've also done the heavy lifting of porting and recompiling, so you don't have to perform any undifferentiated heavy lifting when you're moving over to Graviton 2 instances. Basically, it's a simple scale compute operation. And you can, of course, have a heterogeneous mix of instances. You can mix and match basically your Graviton 2 instances and your Intel-based R5 instances within the same cluster. And then you can have a writer work as your R6G, your read replicas work as R5 clusters. Of course, it's available for both the open source engines, Postgres, as well as MySQL. So for monitoring, we do have quite a lot. Actually, we have integration with CloudWatch. We have integration with enhanced monitoring. we have something called as Performance Insights. So it is fully integrated with CloudWatch. You get a lot of data out of your Postgres logs being sent to CloudWatch, where you can monitor database metrics like volume read IOPS, volume write IOPS. You can set alarms, etc. With enhanced monitoring, you can actually monitor the OS and your host level metrics. So anytime you have enhanced monitoring turned on, you can use your hypervisor metrics for the DB instance, like CPU utilization at the hypervisor layer to actually get those metrics. You can see which thread uses how much CPU, etc. And with performance insights, of course, you get a little bit more. So you get database level metrics, and you get quite a lot of benefits out of seeing what's the load at any point in your database. So primarily the central metric that we use with performance insights is called DB load, and which is collected every second. And this database load represents the average active sessions for the database engines. It's averaged over time. And primarily, you get a bunch of information exposed via Postgres wait events, SQL queries, top hosts, top users, top databases, applications, and sessions that are waiting maybe for something to happen. Maybe they're creating a load on your database and you don't know where to look. Performance Insights actually gives you that capability and helps you there. With security, we have a layered mechanism. So we do have 5 layers of security, and you'll learn a bunch about this if you could just go to Google and Google for the shared responsibility model. We have VPC at the network layer. We have security groups, network access control lists, as well as controlling these restrictions through whitelisting or allow listing, etc., through IP addresses in the network layer. We have data protection, encryption at rest and transit, supported natively. You also get IAM control to your database cluster, so identities and access management through roles, database level roles and policies through IAM, as well as there is Kerberos authentication support. There's also the native RBAC support, role-based access control, tying it together with IAM. And of course, if you have multi-account structures, for example, you can use something called AWS organizations. For auditing itself, we leverage something. We have, of course, natively, we have VPC flow logs, and we have CloudTrail integration as well, where you capture API calls. Each and every API call is being captured in those CloudTrail logs. And we have something called database activity streams, which is another mechanism to basically publish your changes from the database cluster in Kinesis data streams to a third-party integration technology. And this is actually here. So here you will see the changes from your database actually flow through to Kinesis data streams, which is a different service. And then you can use Kinesis data streams to publish changes to either Firehose, or you can publish these changes to your partner database security apps. Specifically, I've seen this on the field being used with tools like IBM's Infosphere Guardium. There's McAfee's Data Center Security Suite. There's Impova's SecureSphere database audit and production tool, which can basically capture and audit your database, primarily used for compliance and auditing purposes. Just a few more slides to go. Migration, primarily when we are talking about migration, you have the native tools, of course. You have pgdump and pgrestore. You have AWS Database Migration Service. This is where we have a different tool which can do heterogeneous migrations. So if you're coming out from, let's say, Oracle, or you're using Sybase, using SQL Server, etc., or you can use Postgres on a different version or a different platform, like if you're hosting that on-prem, or you're using it on EC2 instance, for example, vanilla Postgres. You can also leverage Database Migration Service for migrating from those versions to one of the two, RDS Postgres or Aurora Postgres. You can use, of course, logical replication, and you can use the native one if you have version 10. Or if you have previous versions, you can use the pglogical extension. And of course, if you're already on RDS Postgres, it makes it a little bit easier because there's quite a lot of similarities in the engines. So two easiest ways to sort of migrate from RDS Postgres to Aurora Postgres would be one through snapshot import. This is primarily your PG dump in the RDS world, and you're basically restoring that dump to an Aurora cluster. Of course, a little bit time taking, depends on the size of your database instance. The second is your read replica, and this is the easiest way to do it. My preferred approach, of course, the best practice, because what you can do with RDS Postgres is you can create an Aurora read replica out of it, which is basically a compute instance, one step, and then the next step you can actually, with a click of a button, you can promote that to become an Aurora cluster. So it basically becomes a read write instance. So that's pretty easy, pretty convenient. Under the hood, it's again asynchronous replication, so it makes it a little bit quicker rather than the pg dump, pg restore option through RDS Postgres using the snapshot import. So the last slide, of course, we want to look at what's new in the platform. And there's quite a lot. It's continuously improving. It's continuously innovating. And we have quite a bunch of improvements and innovations, in fact. So not going through everything here. However, you'll notice previously we used to have around 64 terabyte database size. That's been doubled to 128 terabyte. With that comes the dynamic resizing of storage space. So anytime you are deleting data from your Aurora cluster, such as dropping a table or a partition, the overall storage space previously used to remain the same. Now we are dynamically reducing that. So you're paying only for what you're using. We have a fast failover driver, JDBC driver for Postgres in preview, which makes it a little bit quicker for failing over to, let's say, another read replica within the region. There is also a very nifty feature called snapshot exports to S3 in Parquet. So basically, this gives you the capability to export your transactional database snapshots to S3 in the Parquet format, which is an efficient open columnar storage format for analytics. So basically, this gives you the Parquet capabilities and speeds. And of course, it's twice the speed and it's 6 times less in the storage footprint because it's highly compressed. And this data gets stored in S3. So you are now querying your semi-structured, your structured data, and then you're joining this with your data lake data files, and then you can do integration with things like Athena, EMR, which is our MapReduce, Elastic MapReduce service, Redshift Spectrum, or SageMaker for data science workloads. Of course, some extensions. So RDKit is for chem informatics. We have Lambda integration. So this makes your, if you want to write something like we noticed, we saw PGLogical as a stored procedure language. Now you can actually use Lambda, which is a serverless way of running code. So you can use your Lambda functions through your Postgres cluster to actually run certain different things. You can invoke some functions. You can have triggers set on your S3 store, for example, to trigger these functions. And these can trigger your stored procedures. These can have some designated jobs like maintenance, etc., for your database clusters. The latest version for Postgres supported on Amazon Aurora is version 12, major version 12. So we do support in-place upgrade. So there's no more sort of a whole, of course, there needs to be a plan in place to perform this major version upgrade. However, you have this click-through major version upgrade from going from version 11 to 12, which makes it quite a lot easier actually in the Aurora Postgres world. Because if you're going from a previous version, and if you don't have that push button upgrade process, you do have to take care of extensions. Some of them are not backward compatible, some of them are backward compatible. So that is actually a separate way of upgrading those extensions. So there is quite a lot of nuances that go into a major version upgrade. So you do need to pay careful attention. But with the push button from 11 to 12, this actually is taken care of seamlessly. With global database, of course, we saw two enhancements. One was the managed RPO for Postgres, and of course, the managed planned failover for, again, both Aurora MySQL and Postgres versions. So with that, I will wrap it up. I hope this was helpful and you learned something new today. Thank you again for spending the day with us. Thank you to SQL Data Saturday for this opportunity. And at this point, I'm happy to take any questions. Feel free to unmute yourself, or I'll just maybe have Steve read them out through the chat.
I still cannot believe that you are able to push so much info, even though you passed the 60 minutes, but still.
It was quite a lot.
Yes.
It was a ton of info. Yep.
Question: what are the main differences between Aurora and RDS? You can answer that, which is basically managed versus some sort of managed, right? Go ahead.
Yeah, great question, in fact. So RDS Postgres is actually, you can think of it as a managed database platform. However, it does leverage quite a lot of capabilities from the open source community version. So anytime you are used to, let's say, the community version Postgres, for example, the latest version on community Postgres is version 13. GA 14 is also, I believe, going to be there soon. So with the compatibility in terms of the community version, RDS does support version 13 as the highest major version. There's also, whereas in Aurora Postgres, we support version 12, which is a little bit behind. With RDS Postgres, you do get still that, if you think about the architecture itself, you'll get RDS Postgres, you'll get the EC2 instances, which is your R5s, R6Gs with Graviton. And for the storage, you'll actually get your EBS volumes. So the latest and the greatest innovation that we've done with Aurora Postgres is on the storage engine, where we don't use these EBS volumes at all. So you won't see, if you're used to like EBS volume, which is the Elastic Block Store storage, these are by default, these are actually distributed twice. So you have a mirror copy of your EBS volume for high availability and fault tolerance in the same availability zone. So that's where your RDS Postgres is using EBS volumes as the underlying storage, whereas and you actually have to take care of all these replication capabilities. You have to make sure that you have another read replica for your RDS database, which can take on the role of a new writer in case there is something wrong with the primary instance, to have that sort of replicated model and highly available fast failover architecture. Whereas in Aurora Postgres, you have it by default. So your distributed storage engine is actually distributed across 3 AZs, 3 availability zones by default. So anytime you are failing over, you don't have to do any database level changes. Your replicas are still connected to the same underlying storage. The only thing you're doing is promoting, you are flipping over that switch for the read-only node to a read-write instance. So that's much quicker. So there is definitely that improvement in failover time. The third difference is RDS Postgres. Today, we support up to 5 of those read replicas. So you have a limited scaling option there. Whereas with Aurora Postgres, you have up to 15 read replicas. And of course, you don't get QPM, you don't get CCM, so cluster cache management, query plan management, fast database cloning. You don't get global databases with RDS Postgres, because you can think of it as primarily a fork off of the open source. So anytime a new minor version or a security patch or a major version change to RDS Postgres, to community Postgres, that is exactly what we have in RDS Postgres, but as a managed platform. Whereas in Aurora Postgres, due to these different, due to the way the storage engine is architected a little bit differently, there are a little bit differences in the changes and differences in the binaries that are pushed through in the community versus the Aurora engine. So it takes a little bit more time to apply those changes and make that the recently available version available in Postgres to work with, in fact, the Aurora distributed storage engine. And that's the key difference. So there are those engine level and primarily the storage level engine differences between the two engines. Okay, I can also see the chat. So when migrating from on-prem SQL Server to AWS, what are your thoughts on pros and cons via data migration services versus backup restore to take into consideration? Be aware of planning. Awesome question, and definitely quite a lot. In fact, it's a loaded question. And whenever you're thinking of an on-prem any database, think about SQL Server, you can think about Oracle, you can think about any database to any other database, be it AWS, be it any other database. Basically, what we are doing with the database migration service is giving you this capability, which will make a lot of the pains of setting up the pre-planning, like setting up uh, tasks to do data validation tests on your source and target, setting up replication instances, or basically a compute node. You can think of it basically what you're doing with these native tools, like backup and restore, is you're dumping out in a file. For Postgres, for example, you're using pgdump to back it out, or push out the backup dump to a file, and using that file to again restore, using pg restore to read again through that file and populate a new cluster from scratch. So anytime you can think of it as a live production database, and you are taking that backup through these native tools, using tools like pgdump through your live operating database, you need to stop writes, or you need to stop your application writing to that database in order to not actually corrupt that backup file. So there is going to be that downtime, there's going to be that outage. So you will need to be careful in terms of pausing those writes, making with RDS Postgres, what we do is a multi-AZ or a multi-availability option, where we actually promote a secondary AZ or availability zone as a standby, which becomes your primary anytime you have your upgrade process. So your application can still point to that standby server when your upgrade is happening on the primary, and you can have it as a highly available architecture. So with these native tools, there's that problem of incurring that downtime and sort of momentum pause in your day-to-day operations, which of course is not acceptable to a lot of businesses. Whereas with these tools like database migration service, what we have done is through this, there are these two capabilities called bulk load and change data capture. So what we do is you can point your replication instances with DMS. We have these concepts called replication instances, which are basically a compute node we provision for doing the migration itself. It's sitting in the same VPC, virtual private cloud. It has the same security protocols applied to it as your database on AWS. So it's that secure channel, one. It's that dedicated infrastructure, two, which gives you that high bandwidth. Three, it actually connects to your live production database on-prem and does not block the replication channel. So anytime your writes are coming through to the application layer, from the application layer to the database, with the CDC mode, which is the change data capture mode, your database does not need to actually pause those application changes. So your database still continues processing those writes as they're coming. Your DMS, since DMS service is the acronym for database migration service, we basically keep reading those changes out through the CDC. There are these concepts of tasks. So you basically create one task for bulk load, you create another task for CDC, and then through that task, it's actually parallelly read. So there are these different channels, there are these different threads that are created, which do not actually block anything on your primary database instance from happening. So your application is still working real time. There's always writes being written. There is no downtime. You can do literally ongoing migration from your SQL Server or your Oracle databases to your AWS ecosystem in real time. So there are actually blogs. I will probably share them after this session, or I'll share it with Steve, and then we can share it publicly. But if you just Google DMS migrations, you'll just get a list of a lot of AWS blogs that we've written on these topics. So that's the primary benefit.
Oh, Shayon, thanks a lot. Don't know how, but all the questions ended up at the end. But yeah, still great. Thanks a lot for the session.